All right, no music, no fun. We are just going to get to work, knock this out, and then move on with our lives. I will get out of your way. The Fourier, the Merrier, or something like that. So let's do some Fourier series. Or should it be 5e because 5 is more than 4? Fourier, 5e? I don't know. Okay, let's do some work. Whoa, not that much work. The reminder from last time, these were our three formulas for calculating the different components of the Fourier series of a function, for finding its frequency content by saying how much cosine of x, how much cosine of 2x, how much cosine of 3x, so on, do I have to add up to make this function. And looking at these, you're like, man, that looks like a lot of integration. Well, to be honest, it is. Kind of sucks. I'm not going to lie. However, there are things that you can do to make integrals easier. And one of those things that you can do to make integrals easier is to write them in terms of exponentials rather than trig functions. Because if you're having to do all sorts of wacky trig identities to perform the integration, it's going to be a pain. But once upon a time, when we were doing some of the complex number arithmetic, we had these lovely formulas for converting cosines and sines into exponential functions. Complex exponentials, but that's fine. It's whatever. It's easy. You're over it. Complex exponential is an oscillator. Sine and cosine are oscillators, so no problem. And the reason you might want to do this is if the function you're trying to integrate is something that plays nice with exponentials in integration, like polynomials, for example. You can integrate x e to the x with integration by parts, then that might be easier than trying to integrate x sine of x, for example. So when you do the substitutions here, convert the sines and cosines into exponential form, what you end up with is actually just this one single formula. Now, the formula, conservation of difficulty, has become twice as hard because now we are going from n equals negative infinity to n equals positive infinity instead of just going from 0 to infinity. But there's only one of them, so we got that trade-off going on. Anyway, you can write your function in terms of a sum of complex exponentials, each one with a particular frequency, and you can get the component, the magnitude really, of that frequency within your function by doing this integral. Okay, so again, from a practical point of view, I recommend switching to this version if your function f of x is something that is easier to integrate with exponentials rather than with trig functions. Great. Okay. I promised you an example that will be the main focus here. I do want to give you one more calculational tool, trick, something to make some of the problems are a little easier. These functions are going to be orthogonal if they have different frequency content. So this is very, very analogous to what I showed in the previous video that showed that sine of x and cosine of x are orthogonal. It's the same kind of calculation that you do here. And the reason I have to make this point, I also brought this up last time, if something is the same function as itself, it can't be orthogonal to itself unless it is literally 0, in which case, 0 times anything. So, fun little identity here. This actually is going to be one of the expressions where the Kronecker delta shows up, is when we start doing the evaluation of these Fourier series components. When you actually start doing some of these problems, there's an example coming so soon, I promise, you will sometimes get results that look like this, where you'll have two exponentials multiplied together in your integrand. And what you can then do is you can say, aha, I remember my rules about orthogonality. I can jump straight to the answer. And being able to jump straight to the answer instead of doing the integration is a beautiful thing. You gotta love it. So this is a way of essentially logically showing the relationship where if n and m are not equal, they'll be orthogonal, the result will be 0. But if n and m are equal, well, then it's the same function times itself, and when it is properly normalized, then you're just going to get this 2 pi out front from the interval that you're integrating over. Okay, great. Okay, before we do the example, I'm the worst. I'm the absolute worst. I'm actually a little sorry. But 2 quick things that I want to say in very different domains about why it matters, because that is important as well. First, acoustics are important in materials. Like, yeah, I'm a huge music nerd. I'm going to talk about music and composition and signal processing, whatever, and like that's fine. That's not really material science, right? However, in material science, the way materials respond to vibration is absolutely important to their function. You ever been in a really loud car? Be like, wow, this car is super loud. This sucks. I wish I could hear anything. That is an acoustics problem. That's a problem of the materials in the car resonating at certain frequencies. And what that looks like, especially if you've ever been in a car that has a certain resonance to it, and there's just like this sort of concentrated noise that you can't get rid of, then this is a problem that is understood through Fourier series analysis. You're saying, oh, one of my frequency components in the noise spectrum of this vehicle is extremely large. And then once you've isolated that, then you can do engineering work to redesign the vehicle to remove that resonant mode. Or another place where this is really important is actually in fatigue, because vibrational fatigue is very much a thing, like high cycle, ultra high cycle fatigue for materials that are subject to a lot of vibration. You need to know how they respond to different frequencies. And that is, again, fundamentally a Fourier series and Fourier analysis problem of saying, what is the frequency content of the vibrations that my material is subjected to in order to predict its fatigue modes and ultimately how it will fail to design around that. Then in the realm of electronic materials, this is important for a very, very different reason, which is that when we are looking at band structure in semiconductors, so when we're looking at the different energy levels that are allowed in a certain lattice, those energy levels are determined by the frequency content of the lattice. And there's, of course, this relationship, which we saw last time or 2 videos ago in the Schrodinger equation video, about the fact that the energy is proportional to the frequency. So solving for the frequency content of the electron waves that are in a given lattice, which we do this by Fourier analysis, that tells us the allowed energy levels of those electrons, and this is what lets you calculate band gaps and all that business. So really, these are only 2 examples, but many, many problems in materials are better understood in terms of frequencies rather than positions. And that is the core idea that I want to get across here. Also, we're going to do some pretty cool stuff for the last week or 2, and, great. Okay, here's your example. I promised an example. We're going to analyze a square wave. So this is the square wave function. It is a function that is, I'll draw my little axes here. To the left of the origin, it is just a constant value. A stands for amplitude here, by the way. And then to the right of the origin, it is equally constant, but positive. And you're like, that doesn't look like a square at all. Extend the function periodically. Make it repeat. Like, oh, okay. So it's going to repeat, and it's going to repeat, and it's going to repeat. Well, it still looks like a bunch of lines. Connect the dots. Oh, there's my squares. That's what makes this a square wave. So this is one of the starting points in getting used to this series analysis, is taking a function, really drawing it, like I'm not kidding, draw the function, and then say, okay, how do I understand this as a periodic entity? So there's our square wave, and it repeats with a period of 2 pi. I was probably supposed to draw it in the space below, but I'm not smart. Okay, first we're going to find the constant term. So we have an integral. We're going to plug in our function. And what I've done here is to put in the value for the function, splitting up the integral into 2 parts. This is also really common practice in these sorts of problems, is that your function might be defined piecewise. And so you'll have one integral over each piece of the function. In this case, I have my negative piece and my positive piece. Great. Then when I evaluate the integrals, integrating a constant is pretty easy, and I put in my bounds, and then I get 0, which is no surprise whatsoever because 0 is the average value of this function. It spends equal amounts of time above and below the axis. Okay, so our constant term is 0. That's the average value. Great, moving on. What about the a coefficients? What is the cosine content of this wave? Well, we're going to put in the function into the expression. Here's my function. Here's my function. Again, it's broken into 2 pieces because the function itself is defined piecewise. And then from there, we evaluate the integrals. So you integrate cosine, you get negative sine, you integrate cosine, you get negative sine. And when we do all this, you put in your bounds, you evaluate sine at 0 and pi, you keep track of your negatives and positives correctly, and then what happens is you get 0. Okay, well, this is turning out to be pretty easy after all. This is why this is the example problem. But if these things didn't integrate to 0, if they integrated to give some non-zero number, that would just be your component. So the other way you could have known that this is 0 is just by looking at the function itself. The way the function is defined, this is an odd function. It is symmetric around the origin, right? If I draw a line through the origin, the function is opposite on the opposite sides of that. And since this is a purely odd function, it must only have odd components. And since cosine is an even function, that means there's no cosine component to this function. Okay. Now we need to calculate the b components. So we do the same thing. We have our formula, we plug in our function. The function is defined piecewise, so we break our integral up into pieces. And when you put in these expressions, you're like, great, everything cancels out. This is so simple. And then you're like, wait, hold on a second. Why are all of my answers 0, but the function itself is not 0? Have I done something wrong? Well, let's look at this. Being careful about it, I'm not sorry. This expression that we have, when you plug in the bounds on the integral and you evaluate cosine at 0 and pi and negative pi, and you add and subtract carefully, they cancel out, but it depends whether n is odd or even. For even n's, everything cancels out. For odd n's, they don't cancel, they actually reinforce each other. And so you get a plus a plus a plus a in the numerator when n is odd. And then that pi n is still hanging out there in the denominator. So when you're evaluating these formulas, you do need to think about what is the effect of the value of n. Even though it's just a parameter in this expression, whether it's even or odd can often influence the result that you get. And so you need to think about each of these cases. So now keeping track of the fact that a naught is 0, all of the a coefficients are 0, the even numbered b coefficients are 0, but the odd numbered b coefficients, so b1, b3, b5, are not 0. Now we can write down the Fourier series for this square wave. And here it is. So this is the 4a over pi coefficient that we had. And then it's 1, 1/3, 1/5. Each of these frequencies is contributing to the overall expression, and there is a smaller amount of the higher frequencies. So there it is. This is the Fourier series for that square wave. Ta-da! There's your example. I said this was going to be short. I meant it. I'm sticking to my word. So I'm sure you will have questions. That is great. Send me those questions. There will be examples to work through in the homework. And going forward, after you've done just a couple easier ones by hand, then we're going to get into how to do this numerically, do more visualization, do more plotting. And that's where the really interesting and exciting and also really conceptually rich side of things comes in. I mean, doing integrals is good for you, but it only gets you so far. So that's where we're going next. Please look forward to it.